So hello everyone. So welcome to the live session of this uh, NPTEL MOOCs lecture Biointerface Engineering. So I welcome you all for registering this course. So if you have any query, you can post and I will be able to answer it. Good afternoon, Professor Kishore. So we are waiting for a few questions. In between, I can briefly talk about the course. So in this course, as you know, this biointerface basically we are talking about. We are having a surface of biomaterials, and it is going to interact with a body fluid. And in the body fluid, we consider basically these water molecules, macromolecules like proteins and the cells. So interaction between the surface as well as this body fluid or biomaterials. So this we basically consider as a biointerfacial interactions, and few applications like biomedical implants, tissue engineering, drug delivery, and even this addition of pathogens lead to the biofouling. So if you want to tune these desired interactions, so it can be done by modifying the surface, or you can say engineering the surface properties. So what happens when any biomaterials come into contact with the body fluid or biological system? So first one is the intermolecular interactions. These intermolecular interactions lead to uh, the first, you can say that it is like a force between your surface and the body macromolecules. Followed by that, we have the major protein surface interaction and cell surface interactions, and these interactions lead to that biofouling, or it may lead to the successful implant. So in this course, so if I want to go for the biointerface engineering, the first aspect should be we should know the material properties. So what is its chemical properties, what is the physical property, its morphology, and what is the intended function. Let's say whether it is a bone implant, dental implant, or it is a tissue engineering application, diagnostic, biosensor, or drug delivery applications. Then accordingly, either we have to use the engineered materials like nowadays that novel or metallic alloys, these multifunctional ceramics and polymers are available. Other option is you have to go for the surface engineering and the surface modifications. So various physical, chemical and biological methods are available for surface modification, and which in turn tunes the biointerfacial interactions. So also we will have discuss in this course how to analyze the interface. So we can analyze at nano level using various techniques like atomic force microscopy. We can analyze at micro level using simple microscopic techniques, and macro level by visual or the spectroscopic techniques. So these are the 8 modules of this course. So in the first, as I told, in the biointerfacial interactions, first step is intermolecular forces. So in the first module, we have discussed intermolecular forces. Then followed by that, we discuss the adhesion and the wetting phenomena. That whenever a liquid comes on the surface, what is the interaction between that liquid and the surface. Then followed by that, now next comes how we'll characterize the interface. So once we know how to characterize the interface, then we should be able to see whatever the surface engineering is being done, how much it is effective or how much it is implemented. Then the next step of the biointerfacial is the protein surface interactions, so which includes the adsorption of the protein, then kinetics of protein adsorption. And briefly we have discussed as this protein aggregation is related to protein adsorption on the surface. So next module we discussed about the protein aggregation. So far we have covered these 4 modules, and in the next 4 modules we are going to discuss the protein aggregation, and third step in the biointerfacial interaction is the cell surface interactions, and last 2 modules are the surface engineering, what are different physical and chemical methods to tune or modify the surface properties, and also we will see few case studies based on the physical methods as well as the chemical methods for surface modifications. So here is the outline of the module 1. So when we discussed about the intermolecular forces, so we first started the 4 forces of the nature: strong and weak interactions, the gravitational and the electromagnetic interactions, and followed by that we will discuss the historical perspective of intermolecular forces starting from the 17th century uh, to 21st century. Then we saw that in the historical perspective there are controversy, that because if you remember the gas law, so it says there are repulsion between the gas molecules, but when the Newton discovered that uh, gravitational force, so it says it is an attractive force. So because of these confusions, in I think 18th century, my proposed that pair potential. So in the same equation, it has both attractive as well as the repulsive part. Then in the next lecture, we discuss how we can classify the forces and the pair potentials. So there are various ways to classify depending on their opposite natures. So one may be the short range, one may be the long range, one may be the weak force, strong force. But there is some ambiguity because one force, depending on its media, or you can say solvent, it may be weak, and in the other media it may be the strong force. So based on that, what we discussed, it's better to classify based on the strong intermolecular forces and the weak intermolecular forces. So in the strong intermolecular forces, we discuss the covalent interactions and the electrostatic interactions. So this electrostatic interaction, it can be between ion and ion, it can be between ion and dipole, it can be between dipole and dipole. Then weak interaction, we discuss the van der Waals forces, dispersion forces, steric repulsion, hydrogen bonding, and hydrophobic interactions. Then followed by that, we try to combine the first and second law of thermodynamics, and by combining the first and second law of thermodynamics, related the work with the mechanical work along with the interfacial work, electrical work, and these works, particularly the interfacial works, we are able to relate it with the energy component. And from there, once these intermolecular forces are related with energy and energy is related with the uh, surface tension, then we can relate these intermolecular forces with the various physical and chemical properties like its solubility, its charge density, and its solubility, its charge density, and also we discussed how if you vary the different solvent, how the interactions, or you can say that using this Boltzmann distribution, how you will be able to say if material is going from one phase to another phase, how it will behave like, and also we quickly discussed about the chemical potential. So in the next week, after understanding the intermolecular forces, we started, let's see what is the surface energy and what is the work of radiation. So basically this intermolecular interaction, it may be between uh, two same medium or two different medium. If 1 and 2 are the same, if 1 equal to 2, so we call it cohesion, and if 1 is not equal to 2, we call it the adhesion. Then what we found was this work of adhesion, W1 work of cohesion is twice of the surface tension or the surface energy, and similarly the work of adhesion is also related with the surface energy. So work of adhesion between 1 and 2 is sum of surface energy of 1 plus surface energy of 2 minus interfacial energy of 1 and 2. So accordingly, if you want to calculate the work of adhesion, so we should know the wettability, and using the Young's equation, this contact angle is related with the interfacial tension. Then we saw the surface may have physical and chemical heterogeneity. How to incorporate those heterogeneity to understand the actual contact angle or wettability. So for the physical heterogeneity, we discussed the Wengel equation. For chemical heterogeneity, we discussed the Cauchy equation. Then followed by that, we discuss about the cohesion, adhesion, and few applications of adhesion in the biological systems. Then in the third module, we have discussed how to characterize the interface, because if you are modifying or doing the surface engineering, then we should be able to understand whether it has been implemented or not. So the first thing is how to characterize the contact angle, how to characterize the surface tension. So for surface tension, we discuss the detachment path method, drop shape method, and the dynamic method. For the contact angle, so the first part was for the surface tension, and for the contact angle, we discuss the sessile drop method, Wilhelm's plate method, and porous plug method for the powder samples. This is for the contact angle or wettability. And in the third lecture, we discuss that how we can analyze the surface energy of solids, because whatever method we discuss in the first part, that is only applicable to the liquid samples. So for solid samples, either we can go indirect method, means by measuring the contact angle of two different liquids of different polarity, one should be polar, one nonpolar. Then from that contact angle, we can apply the Young's-Dupré equation to determine the surface energy of solids. So in the fourth module, that was the second step of biointerfacial interaction, that is protein surface interaction, and we discuss first brief introduction about the proteins. So proteins are basically, they are polypeptides made of different amino acids, and amino acids, as they are of the four different nature, it may be the hydrophilic, hydrophobic, positive charge, and negative charge. That's why they give the complexity to the protein molecules. So we discuss the function of different protein, the stability of the protein, and apart from the non-covalent interactions, what are different other interactions like hydrogen bonds, hydrophobic interactions, which play crucial role in the stability and the function, or you can say the folding of a protein. The next comes, if there is a protein surface interaction, then how we can characterize it. So we discuss different method to measure the adsorption amount, this solution based method, as well as the instrument or the analytical techniques based methods. Technique based method. So in the case of protein adsorption, both things are important. One is the what is the amount of protein, and second important thing is its secondary structure, or you can say the conformational changes. So for the amount, as I discussed, we can use the solution depletion method or various instruments like quartz crystal microvalence, surface plasmon resonance, and for the secondary structure, we can use the FTIR or circular dichroism. Then, if I want to tune or engineer this protein surface interaction, so I need to know the kinetic parameters. So I discuss how we can model the protein adsorption kinetics, and based on that we should be able to estimate the kinetic parameters. And also we discuss, because when we talk about the body fluid, so it has a mixture of proteins. So during the adsorption, always there is a competitive adsorption. So one example of the competitive adsorption is the Roman effect. So we says that larger protein molecules displace the smaller protein which are pre-adsorbed on the surface. So what happens? If we are having two different size of protein, so a smaller protein is having higher diffusivity, so it will reach to the surface fast. Then larger protein, when it comes, then it displaces or replaces the other smaller protein. So that is the Roman effect. So after that, this next four modules, this protein aggregation. So we'll quickly discuss protein aggregation, particularly in the presence of surfaces, because for the protein aggregation, the first step is the protein unfolding, and that is related with the protein adsorption. So next module we'll discuss the protein aggregation. Followed by that, we'll discuss the third step of the biointerfacial interaction, that is the cell surface interaction. So in the cell surface interactions, we will discuss what are the host responses to biomaterials when they are implanted or they are applied. Then what are different cell adhesion mechanisms, and finally we will discuss how biocompatibility of a biomaterial is defined and how they are analyzed experimentally. Then followed by that, in the seventh module, we will discuss what is surface modification, what are the importance of surface modification related to tuning the biointerfacial interactions. Then what are different physical, chemical and biological methods for the surface modifications, and also how to characterize these engineered and modified surfaces using various spectroscopic and microscopic techniques. And then in the last module, we will discuss one chemical method, particularly formation of various self-assembled monolayers. Then there are also two case studies. One case study based on the physical modification of surfaces and their biointerfacial interactions, and second case study is based on the chemical modification of surfaces and their biointerfacial interactions. So the objective of this course is we should be able to understand the various insights of biointerfacial interactions, and at the end we should be able to apply this interfacial engineering or the surface engineering to improve, or you can say design the novel biomaterials. Apart from biomaterials, it can be also applied for the other application like antiviral coating. It can be applied for the targeted drug delivery. It can be applied to the biosensor. So these are the text references. So I will just see if there are any queries so far. So previously we have received few queries, so I would like to talk about that. The first thing was one query related to the spreading coefficient. So spreading coefficient is basically the difference between the work of adhesion and the work of cohesion. And as we know, this spreading coefficient that, or you can say the work of adhesion and cohesion is a function of the surface tension. So if you can tune the surface tension, you should be able to tune the spreading coefficient. So that's why if you just see how biosurfactant works, so basically what biosurfactant is doing, it is able to tune the surface tension, or you can say it is able to reduce the surface tension. That's why it is tuning the spreading coefficient. And the next question was effect of the roughness. So as I told, the roughness can be of two types. It may be the chemical heterogeneity or the physical heterogeneity, and in both the cases, in case of physical heterogeneity, we have to apply the Wengel equation, and in case of chemical heterogeneity, we can relate the surface energy with the Cauchy equation. And third question was whenever there is a whatever we are measuring the surface tension or the surface energy, whatever we are talking about, it is related to the either this is a static or the dynamic parameter. So basically, whenever we are talking this surface tension or surface energy, we are not considering the kinetics. Basically, we are considering the equilibrium part. So that can be achieved either a slower process or the without any external mass transfer. But when we are talking the surface energy of water, means it is the equilibrium surface energy. And the next question was that the protein, as I was talking, the proteins are made up of different amino acids, and amino acids can be classified into four different categories like hydrophilic, hydrophobic, positive charge and negative charge. So depending on a protein, if there are more hydrophobic amino acids, so it is considered as a hydrophobic protein. If there are more positive charge amino acids, it is considered as a positive charge protein, and accordingly the intermolecular interactions between the protein and protein surface varies. So as we know this, whenever protein comes on the surface, so the main intermolecular interactions are first is of course by default it is a van der Waals interaction. Then next is electrostatic interactions. So it depends on the what is the charge on the surface, what is the charge on the protein. Then followed by that, the next interaction is the hydrogen bonding and also hydrophobic interactions. So if there are more hydrophobic amino acids, so they are going to have the more hydrophobic interactions. And in many cases, if you are having the hydrophobic surface, so what happens because of the favorable interaction, as we know this delta G is a function of enthalpy and the entropy. So if enthalpy is not favorable, then what happens that in order to make the process happen, it is compensated by the increase in the entropy. And whenever there is increase in entropy, means the randomness is increasing. So protein molecules try to reorient themselves or unfold themselves so that they can reach to surface and interact on the surface. So these were few queries which I have received so far. So I'm just waiting for any more queries. So as I have not received any queries, so thank you very much. So we'll have one more live session, and in between I request to send your query beforehand, so it will be easy for me to prepare written answer and explain in more detail. And I hope that all of you are enjoying this course, and I wish a great learning in this course. So next 4 modules are the left. Followed by that, there will be a exam. So I wish all the best to whoever is appearing for the exam. And I always welcome any suggestion or any query, and I will be happy to help or happy to answer those queries. Thank you.